My name is Tina Grotzer, and it's a pleasure to be speaking with you today. I started this work I started this work many years ago, but when I first began, it was as a classroom teacher, so that's probably the most important part of my bio, because what I did was I looked very closely at how the students were learning science and how many wonderful teachers were teaching it using best practices and everything that we know about teaching science well. However, the students were still struggling to understand it. So that was what got me first interested in doing this work and starting to look at what was going on and how we could help people in these classrooms. The initial impetus for this came, as I said, from watching in the classroom the ways that students struggle to understand science concepts and how even with good teaching, they would come back to their initial ideas and revert to simpler explanations. So looking at the research, there was about 40 years of very careful research in science education, but also in math and social studies, looking at what we call naive explanations, alternative conceptions, misconceptions, lots of different titles. The reason for the different titles is because even though they result in mistakes in understanding, they come from students' sense making. And we want to encourage our students to make sense. That's a good thing. So these different titles reflect differences in the field about how we should think about them. They also reflect the idea that in science in general, even scientists move from understanding something at one level, and then they gather more evidence, and the additional evidence might lead them to shift their explanation. So scientists trade up for more powerful explanations over time, and we see our students doing the same kinds of things. So these understandings, these naive explanations, are robust. It's hard to extinguish them. It's hard to get students to move beyond them. This research also showed that there were significant differences between the way that students were understanding the concepts and the scientifically accepted explanations that they were learning in school. And interestingly enough, many of the teachers held ideas closer to how the students were thinking than the way the scientists were thinking. And having been a classroom teacher, I completely understand that. I do too. We all live in the world and we come up with certain ideas. And so one of the first things we did as part of this project is we worked very closely with the scientists to figure out what kind of thinking do we want students to do and how do we want them to shift. And I was learning a lot about deep understanding in the science too. So, when you see these misconceptions, it would be very frustrating for teachers because they would see them both pre and post instruction, despite doing good, hands-on, minds-on, often inquiry-based, very thoughtful instruction. So I'm going to change the slide here. So we learned some things about this, that these ideas that students are developing come from a very early age. They're looking at how the world works. There are certain things that they see that they make sense of. So for example, it looks like the sun rises and moves across the sky. We don't have the perception that, we're on a planet and the planet's moving very quickly right now. So these ideas fit with their perceptions. They also learn what different science words mean, and in lay contexts, we often use words in ways that are very imprecise and would lead them to interpret those words in ways that are non-scientific. They're strongly held. The other big idea is that they're often sensible and coherent from the learner's point of view. So there's no reason why students would think of the coat that they put on when it's cold outside in the same category as insulation in a house or ideas about heat transfer and thermal equilibrium. Those are all different categories for kids, even if a scientist would see them in the same way. And of course, this is different from how scientists would view it. So, causality comes into play in everyday life and in everyday science. All of the questions that you see on the slide right now, as simple as they seem, have a lot to do with, our understanding of them has a lot to do with how we reason about causality. As simple as what makes the juice go up in the straw when you drink from it. So, kids will often tell you that I suck on the straw and I make it come up. It's very agency oriented. It comes from their sense of efficacy. I can do this. I can make the juice come up. But a very different causal model underlies drinking from a straw than sipping on the straw and making it come up in a simple linear way, which I will share in a bit. So for all of these questions, you see that they seem kind of straightforward. Many of them are things that you would even study in elementary school, but they all go far beyond simple linear causality, the idea this thing makes this thing happen. So we did a lot in these classrooms to try to understand how students were thinking. We got them to make their thinking visible. We had them drawing models. We had ongoing assessment in the context of a teaching for understanding broader framework. This is all best practices in science education, and so we really were trying to get at how they were making sense. But one of the puzzles in the research is that often we have, as I said, this sense of evolving models, the same things that scientists grapple with. So as we asked students about their ideas, we saw in the first drawing, you see a simple consumer source model or idea, that simple linear model, that energy goes from a battery to a bulb and it makes the bulb light up. This makes that happen. The second model that you see there, we actually call double linear because the students have studied static electricity and they think that electrons move up one side of the wire, protons move up the other, and they clash in the bulb to make it light. So this idea is an idea that fits with what we know, what the understandings that we want them to have around static electricity, but it's not how we think about a circuit. And so even though it's really good thinking, it's not where we want to leave them. The third model at the bottom shows what we call a cyclic sequential model. And that model is the model that most of the teachers we worked with held. And I think, everybody in our research team held that idea at first too. And that's the idea that the circuit is empty and it fills up and then it gets to the light bulb and then it goes back around and it gets recycled. That idea leads to a number of misunderstandings, but they can be hard to detect. And then you see more sophisticated models. So the model over to the side on, I guess it would be your right-hand side, that we call a cyclic simultaneous model. There are electrons and protons all along that wire. And when we hook it up to the battery, they move. And that pushes students to a systems thinking model about the circuit, as does the one above it, which is actually a differential model. So what this shows is that in any classroom, students could have any one of these ideas, and that we need to try to encourage them to put their thinking out there so that we know that, what model they hold and how we need to help them understand. So the challenge that we were trying to solve in our research was that, let's see here. Despite this minds-on curriculum, active processing and modeling of concepts, students still reverted to their earlier ideas. Why were they so robust? Scientific explanation assumes this extensive repertoire of models. But students have very little opportunity to learn it. They have this everyday knowledge that they're bringing, and it serves them pretty well in the everyday world. But as they're trying to learn about scientific explanation, They need to know when to let go of those more simple ideas, like a simple linear model, and when they need to go to a more complex model. So the question we asked was, might limited notions of causality be contributing to their understanding? There we go. Came on the second one. So I'd like to pause for just a moment. And I want you to think about, I've said a couple of things about cause and effect in science in connection to science learning, but I want you to take a few moments to just jot down a few ideas of what comes to your mind. You know, I gave an example in simple circuits, but you might be thinking about other topics. So take a few moments for yourself and just reflect about what it means to you.
Tina, are you seeing the...
I am here. I'm waiting and I'm watching things come up. I'm giving people a moment to think. Okay. So one of the things we're very good at, Dan, at Project Zero is think time.
Right.
All right. So I see that people's answers are popping up, and I see some things about sequential activities and sort of the natural order. Okay, I see some things about action and reaction. All right, very nice. So causality is often talked about in terms of cause and effect. And one of the puzzles about that is that it emphasizes more of a sequential, this happens, then that happens kind of notion. You have the cause and the effect, and they're separate. So as I talk a little bit about the ways that we make sense of causality and some of the patterns that we found in the students' thinking, listen for how that the kinds of ideas contrast with this more distinct notion that the cause is one thing and the effect is something else. Because in some of these models, it is actually blurred in interesting ways. So first, I'm just going to put a little picture up, a little teaser. So one of the things that we love about our contrast between everyday causal thinking and scientific thinking is that we live in the world. And so whatever we hold in our head for the frames for cause and effect or causality, it influences how we behave. And so one of my favorite things is to go around and collect things like this picture. These are all over the streets in Cambridge and Boston. And basically what it says to us is, okay, so in your everyday thinking, as you're walking around being so busy and being very efficient, you kind of make the world smaller than it is. You're focused in front of you. It's egocentric in a justifiable way, I would say. We can't take in all the information that comes to us. It would be overwhelming. So we make the world smaller. So let's talk about how we make the world smaller here. So in our everyday causal reasoning, we do notice patterns that are in our attentional space, right in front of us, like, right around us. So we notice when one thing makes another thing happen, and we do sum across those experiences to seek out patterns or correlations between events. So notice that's about pattern. It's not about causality yet. One of the issues with noticing these patterns is that we don't always remember what we see. And sometimes, like the fish on the previous slide, the fish is in one attentional frame and the outcome is in another. And that makes it tricky to put the two together. But one of our tools here is this noticing of covariation, and that's really important. But the next thing we do is we seek out plausible mechanisms or explanation for patterns. If we just stopped at patterns, we would be focused just on correlations. So we need to say, well, is there a reason these two things are connected? So for instance, if every time you eat at a certain restaurant, you don't feel very well, you probably would notice that pattern pretty quickly because it would, nausea is one of those things that gets your attention. So you might notice that there's a pattern, but then you might ask yourself, well, why might this be happening? And if what you always got when you went to that restaurant was something that was undercooked or raw, you might say, oh, maybe it's connected to the kind of food I'm choosing, and maybe there's something there, and that tells me about the mechanism. So these are very common things that we do every single day in the world. But we pay attention to ourselves. We pay attention to what we think. So the example I gave with the straw, we pay attention to I suck on the straw and the liquid comes up, the role that we can play. And this comes from being a very young infant. You reach up and you knock at a toy and it makes a noise. From the time our students are in the crib, they call out, because they're hungry, and eventually someone likely comes to help them. So we also tend towards efficiency. So we draw the boundaries somewhat closely because it's not adaptive to draw them widely. And then finally, whatever patterns are meaningful to us, we go back to those. We notice them again and again and again. And this is our brain, the research in neuroscience shows that the patterns that we use are the patterns that we are more likely to see in the future. So that's some of the research on confirmation bias shows that we default back to similar patterns that we agree with and are comfortable with. So we started a project in 1998 called the Understandings of Consequence Project, but we also have a current one called Causal Learning in the Classroom to look at how these everyday understandings interacted with the science. And an overview, we saw that students were making these simplifying assumptions and that typical instruction didn't help them to restructure their assumptions. But if we gave them activities and discussion to reflect on their assumptions and restructure them, all of the students performed significantly better. And interestingly enough, it was our lowest level achievers who made the most dramatic gains. They had the furthest to go, but also it was in relation to kind of using their friends' minds well and making what's abstract and what's up here available for them to think about. So some of the more capable achievers might have already been making different assumptions about causality as they learned the science, but having somebody make it explicit was very, very helpful to them. The other thing that we saw was that students were able to transfer the gains from structurally similar concepts to other ones that were structurally similar, but also with support to non-similar concepts. So they started asking, what kind of causality might be in here? Am I making any assumptions? In cognitive science, we call that preparation for future learning, and it's a form of transfer. What patterns did we look at? We tried to teach them 6 different patterns. We didn't have to teach the first one, they started there. But the second one, we taught them that sometimes causality was more domino-like. You had to look further, so it was extended linear. So I'm trying to do it for you for the right angle here for the camera. So it would keep going, extended linear. But we also taught them that sometimes there was mutual causation, and this starts to diverge from this idea of cause and effect. So with mutual causation, it may be an attraction between two things. Sometimes you see it in symbiosis and biology concepts, but sometimes the two things, either the causal force is located between them in some way, or they impact each other, which is kind of like a two-way, little bit different idea. And then we also looked at cyclic causation. Cyclic causation is an instance where you need the cycle to continue to drive things and continue to make it happen. And you really can't break it apart. As soon as you've broken it apart, you lost something essential. So, how can non-scientific teachers? Okay, so I see a question from Gail that I'm going to try to loop in if I can. So the next one here we have is spiraling, and we originally called that escalating, and the students said no, because it can go up or it can go down. And this is actually one that they adopted and used quite often in their own conversation. So they learned about cyclic causality in science, and one group of kids came running out in from the playground and told their teacher that they needed help because they had spiraling causality on the playground because two kids were getting in a fight, and they recognized that at each turn there was an escalation, and that, you know, in those instances it's hard to predict at one level what might happen at another level, but they certainly knew they had spiraling causality on the playground. And then the other one there is relational. And relational is a causality where you have a relationship between two variables that leads to an outcome. So we'll talk about that in connection with sinking and floating. We also found that there were assumptions that they were making, and some of these assumptions make a lot of sense. So for example, number 5, if you can't see something, if it's non-obvious, you're less likely to pay attention to it. When there's an obvious cause, we focus on those, and only in the lack of an obvious cause do we then start to look for a non-obvious cause. Another example, sequential versus simultaneous. So some of you had sequential activities in your cause and effect model. Think about the shift in the simple circuit. When you have a circuit, you hook it up and the whole thing moves at once, like a bicycle chain or like a tire. It's not that this moves before this and then this and then this. And if you try to make it sequential, it leads to misunderstandings. So in electricity, for example, kids will think that one bulb will light and get more electricity than others. They will think that one will light first. And they'll have difficulty understanding Ohm's law, parallel and series circuits, things like that. So these are all patterns that we saw, and some of them make a lot of sense, in terms of, local versus spatially distant. You're obviously going to pay attention to things close by before you pay attention to things far away. But some of them are also counterintuitive. So if my action here contributes to climate change and I'm impacting polar bears far away, I need to know how to think about that, even though it's very different than the way I would normally think about these things. So these are some of I already talked about the battery example. Here's a straw example where the student is focused on that simple linear idea of sucking and making the liquid come up. And here you also see, this is a child's notion of the food web, and they weren't quite sure at the end. At first they were going to draw it back to the sun, and then they said, no, it doesn't really go that way. So this is kind of a line laid out in a circle, and the child has some ideas about energy transfer here, but perhaps not the recycling of matter ideas. This is one idea, not others. So in the classroom, we thought, well, how do we help students see when the causality that they hold is very different than the causality that's embedded in the scientific concept? And so we shared with them something called recast activities. I'm also going to talk a little bit about the power of narrative and why it's important to develop a language of causality. So stop for a moment and think about the sinking and floating question. So what are some things that your students would say about what's going on when an object sinks or floats? Now I'm going to pause there and let you just think and jot some things down.
This is Dan.
Okay. So I'm seeing a variety of responses, and some of them come from a buoyancy model, upthrust. Others, they're focused on the liquid. Lorena mentioned the liquid, but a number of them talk about the object being heavy, and that they're thinking about light and heavy. And what students commonly do, most of them, is they focus in a linear way on the object, and they talk about, or you know, whether it's heavy or light. So it's a simple linear, this makes that happen. And so the overwhelming number of students who hadn't necessarily focused on density as a relative concept, and I see some of you are thinking about it here relative to the liquid, and the what's more dense and what's less dense. But the students start with a focus on the object, and typically, and they focus on whether it sinks or floats. And interestingly enough, unless you tip them off in some way, most students think about the liquid as water. So in a recast activity, what we're trying to do is we're trying to push the students' attention to the relationship here. But we have other recast activities that try to illustrate other patterns, and the idea is that something about this activity will reveal the causal structure so that they're restructuring their understanding. I'll say more about that in a little bit and how it's different from a typical discrepant event in science. But one of the things we do is we give them 2 beakers and 2 pieces of candle, and we ask them what will happen when we drop the candle in. One piece of candle is small and one piece of candle is big. And we drop them into the beakers, and they say, yep, that's what I think will happen. The little one is smaller and it weighs less, and so it floats, and the big one is heavier, and so it sinks. Then we swap the candles. And here they first say, oh, you tricked us. Or they kind of shake their heads and they say, well, wait a minute, what's up with the liquid? So now what they're doing is it's pushing their attention to the liquid, and that's the non-obvious variable here. They notice the object first, they make an assumption about the liquid, and here they have to attend to the liquid. And when faced with this concept, they realize that there's something going on with the liquid, and that the liquid is part of the causal equation here, that they can't leave it out. And so then what we do is we introduce the idea of a relational causality, that it's either a relationship of balance or imbalance, and that they start to realize that they have to reason about the relationship between the two. So why is this concept so important? So relational causality and this notion of sinking and floating in relation to other things explains many, many other things. So it explains the layers of the atmosphere. You know, why does one layer float on another? It explains some things when you have pressure differentials, what happens. So there are many, many concepts that it explains, and there's things that they deal with too when they're trying to wash out. We talk about, when you're washing out a bottle of oil, cooking oil, why you don't fill it with water and then turn it upside down. It doesn't, can't get it out. And they also tend to have lava lamps, the kids, where the lava floats and sinks as it heats and cools. So then we start to connect it to other things. But if you think about how this concept is taught, much of the time it's taught as sinkers and floaters. The kids are taught in a way that fits with their simple linear model. From the time they're in kindergarten, first grade, second grade, many of them are making lists of sinkers and floaters. And I don't have it in my slide here, but there are some very well-known science curriculum out there that actually are labeled sinkers and floaters. So we really want to push students' thinking to see that it could be, that the model, the underlying model of causality is different. So how does this relate to discrepant events? So discrepant events are a concept in science where you do something that surprises students and kind of catches their attention because it's not what they would expect. Well, recast activities are definitely a form of discrepant event, but I would say that they're a very special subset because they illuminate the causality. So here, if you look at these two glasses with water, you see that the first one has two pieces of wood in it, one sunk in the water and one floated in the water. So the one that's floating is rosewood, and the one that's sunk is ebony, and that ebony has a density greater than 1.0, so it's sunk in the water. Not all pieces of ebony do. The other example, it has pumice, and then there's a piece of, I think it's granite, actually, it's a rock from my backyard. So in that one, kids are surprised to see that there are some rocks that float. They expect rocks to sink. And in the first one, they're surprised to see that there's some wood that sinks. So, they know when it gets waterlogged, it might sink, but they don't expect it to sink when it's dry. This is a discrepant event, but it is not a recast activity. And the reason I say that is because the outcome surprises them and it shifts their category understanding a little bit. They'll say, oh, some wood sinks. Oh, some rocks float. But it doesn't change the way they think about the nature of sinking and floating. So the other thing that we try hard to do with the students is to invite them to really talk about what's going on in these different examples and to use the language of causality. I don't know about in your primary language, but in English there are not good terms to talk about causalities that are more complex than simple linear. And we tend to have a very linear mindset. And so students helped us actually invent names. So when we talk about domino causality, that came from our third graders who were thinking hard about these things. But so we use the language and we really grapple with the kids about what it means, because sometimes they'll talk about relational causality as you have two things, but they'll just add them together. So then here, you see the student reasoning that it's really the relationship between them. We also, I said that I would say something about the power of narrative. We also tell them compelling stories about these different concepts. So I don't know if any of you know the story of Lake Nyos, but Lake Nyos was a lake in Cameroon. It is a lake in Cameroon. And at Lake Nyos, one night in the 1980s, nearly 1,800 people did not wake up in the morning. They had died. And when investigators came, their first assumption was that someone had done something, that this was a terrorist act, and that something had been sprayed, some poisons, etc. But no one had seen anything, and there were some people who were still alive around the shores of the lake. And so people started investigating, scientists started looking at what they did understand, and eventually what they learned was that Lake Nyos sits in a volcanic region, and what happened was that the volcanic gases were collecting under the water. And when the lake temperature changed enough to have lake overturn, it released the gases. And once the gases came out, they were more dense than the breathable oxygen. So the breathable oxygen just floated above and sat up above the dense gases. And so the people around the lake actually suffocated. And if they were how many feet up, they could have been fine. They would have been able to breathe, but they couldn't. And so, as we think about that, there's a relational causality in a powerful example that makes you realize how important the layers that we have are and the relationships that we have are. And I think it also helps kids see that sometimes we're quick to think about an agent. Somebody intentionally did this. But in this case, it's part of the environment that we live in and the balance of that environment. We tell other stories for other kinds of curriculum. So in our ecosystems curriculum, we often tell this story about parachuting cats into Borneo, which is a story about when the World Health Organization went in to try to deal with a sickness there, and they sprayed DDT, and in doing so, they killed all the geckos and that would eat insects, and then the rats. The cats died as well, rats flourished, they had all sorts of other problems, so they actually ended up having to parachute cats into Borneo. So these are powerful narratives that sometimes help kids build onto and understand the new concepts that they know in some ways as tacit knowledge up here, but they don't know it explicitly. So I want to stop for just a moment here and ask you to reflect again for a moment about how often you think you use the language of causality in your classroom. Understanding that there aren't that many words to talk about it, but think about whether there are some that you use. So I'm seeing that a lot of you do use the language of causality, which is great. I think it's really important. And, also, it's so embedded in the way that we talk about something making something else happen. So it's really starting to think about how do we broaden the ways that students think about it and whether there are other kinds of patterns that we want them to recognize. We had some outside evaluators scoring some data for us a few years ago, and they said, well, we don't know what to score because kids speak, well, the learners speak causally all the time. This made that happen. So, and they saw that, as Paul just wrote, everything is related. So there is that mindset and bringing that mindset to it. And then it's how do you tease it apart to talk about the causality in the concepts that you're focused on. So I just want to say a couple of things about terms or concepts to be a little bit careful with, I think, in this work. So there's this idea of cause and effect versus causality, and how we use one to talk about distinct causes and effects, but that we can also have attraction, gravitational attraction, forces. We can have things where it's not really this then that, but where the causality is a pattern, and they're not distinct. The other thing that comes up a lot in our work in the environment, we do a lot of work in ecosystem science, and we're working a lot with ecosystem scientists now, developing some virtual worlds that the kids can go into and learn about pond and lake science and things like that. One of the interesting things that comes out of this research, and there's also a rich literature in cognitive science about it, is that we tend to focus on events. When something happens, it grabs our attention. We've kind of been going through sort of low-level processing things, and then something jumps up and grabs us and gets our attention, and we focus on it. Well, events can be problematic if what is happening is a process that takes place over time. So in the biological sciences, particularly as you're teaching it to older kids, but even with younger kids, we try to focus on events in the context of processes. And we talk about events as something that get us to pay attention, but maybe that doesn't mean that something just happened. Then we need to look over time. We might need to look in space and time to understand what's going on. So if you think about an example, when a terrorist act happens, it grabs our attention. We pay attention. When a hurricane occurs, we pay attention. But a lot of these things are, they're going on all the time. There are things happening. You could talk about recruitment processes for terrorism activities. You can talk about collecting carbon for climate change issues. So these are things that happen in space and over time. Now, politicians like events because they garner public support. So if a big event happens, they can be pretty sure that there will be public will to address it. But what that means is that sometimes we're focused on things that got our attention, but may not be as big as they may not be where we should be focusing our attention. A couple of quick examples. When a bridge fell down in Minneapolis, all of a sudden, we were monitoring bridges and looking at the state of bridges and fixing bridges in this country. The bridges had been in disrepair for quite some time, and we had the equipment to monitor them over time, but we didn't until a bridge fell down. At Lake Nyos, they now gas off the lake. There's a webcam focused on it. You can go online and see it. They are constantly gassing off the lake, paying attention to the processes and steady states of the volcanic gases under the lake, rather than waiting for another event to grab their attention. So so it's paying attention over time and putting it in that broader context. There's also a lake in Rwanda, Lake Kiva, has 1 million people living around its shores, and they're still not paying attention to the processes and steady states. The last point I want to make here, I'm looking at time, so I'm going to need to wrap up soon here. The last point just has to do with reliability versus summing across events over time. Sometimes things don't happen reliably within our attentional space, and we do teach students that science experiments should be reliable, which they should be. But if it's something that doesn't consistently happen, then we need to teach them to sum across patterns in terms of the causality. So I want to just share with you some resources, and then I want to stop to ask questions. We have a website called Causal Patterns in Science, and it has many resources on it. It has examples of all the kinds of causality that I've talked about. It has little videos of things happening where kids can talk about and learn about the kinds of patterns and what they are. It also has an area for assessment for people who want to assess, and it has some resources. So I'm going to say more about those resources in a moment. It's linked to our lab website, and here we have papers and things for people who are interested in the back end of the research. But on that teacher website, the causalpatterns.org, we have a number of curriculum units. And these units are designed so that the students are learning the science, and then the causality stems from the science. So they'll see a need for it within that context. So it might have something, I don't know if you could see me, but it might have a page that talks about what is relational causality, but then it would also explain relational causality in terms of density or whatever the concept is. And I've used relational causality as an example. There's other kinds of causality that we talk about. The other thing that we have is a unit that looks at the patterns and then allows you to infuse them into different topics. And we did this because we have a lot of teachers working with us who want to know, how do I apply these things to social studies or language arts or other areas? So we created a set that's really more generic and focuses on the thinking in those patterns. And if you know some of the arguments in critical thinking, it's, should it be situated in the context of the science or the social studies, et cetera, and then pulled out from there, or should it be taught as a generic concept and then applied? We're agnostic on that. We think it could go both directions in the hands of good teachers and invested learners. We also have a unit on the nature of scientific thinking, which some people find helps. It has some research on modeling and a lot of activities around modeling. And then in addition, we're about to release some new modules. And these are more about the features of causality. So the idea that you can have causes and effects that are separate in space and time from, and in different attentional frames. And also that you can have distributed causality, people all over contributing to one outcome, even if they're unaware of it and they don't intend it. So those are some things that are soon to come out, and we invite people who are interested to look at them. I also have a book called Learning Causality in a Complex World, and it talks about each of these patterns, gives lots of examples from the classroom, and those examples are across the curriculum, so people can see connections to topics they would be teaching. And finally, I don't have a slide on this, but I will mention that we have been involved in the last few years developing something called EcoMove, EcoMobile, and EcoXPT. And these are virtual worlds that students can go into and try to solve problems. We don't give them the problem right away. They have to notice the problem, because they pay attention to an event and then they realize it's been happening and they should have paid attention to the processes and steady states going on. But they can time travel back and forth to see what they missed and what they got. And they actually are trying to solve some problems at a pond. And they then start to put the picture together, and they learn some things about causality, that they need to pay attention to change over time. They need to pay attention to distant causes and effects. Distant forms of causality, and they learn the science as well. So they're learning the causal dynamics of the science that's playing out.